Concrete is the most important material we barely think about. It holds up the bridges you trust with your life, the buildings you work inside, the pipes, tunnels, parking decks, everything that quietly keeps civilization running. And yet concrete has a problem we've never truly beaten. Cracks are not an accident. They're guaranteed. The only question is whether those cracks stay harmless or become a pathway for water and salts to reach the steel inside and start the slow, invisible failure process. Now imagine a concrete that doesn't just resist cracking, because no concrete does that forever. Imagine concrete that reacts to cracking the way skin reacts to a cut. It seals the damage before it can spread, not by sending crews, not by injecting epoxy, by triggering a built-in repair process inside the material itself. This is real research and real engineering. Concrete designed with dormant microorganisms and nutrients that only activate when water enters a crack, then mineralize it shut. It's not magic. It doesn't make buildings immortal, but it could change the economics and safety of infrastructure. Fewer repairs, longer lifetimes, and less cement poured over the next century. So how do you put repair inside a rock-like material? And what are the real limits? The ones that decide whether this becomes standard construction or stays a niche technology. Concrete is everywhere because it works. It's cheap, strong in compression, and easy to shape. But the cost isn't just money. It's emissions and maintenance. Cement production is a major contributor to global CO2 emissions, and a huge part of that burden comes from how often we rebuild, repair, and replace concrete infrastructure once cracking leads to corrosion and damage. Extending service life doesn't just save budgets. It reduces the need to pour new cement as often. And maintenance isn't a small problem. Cracking drives water ingress. Water enables corrosion. Corrosion expands steel. Expansion forces more cracking. And eventually, you're not repairing a crack. You're repairing a structural system. So the stakes are simple. Can we keep concrete structures functional longer? Can we reduce life cycle costs and disruption? Can we cut the emissions tied to constant rebuild cycles? Self-healing concrete doesn't need to be perfect to matter. It just needs to reliably seal the kind of cracks that start the failure chain. That's the key, not never crack. Crack, then recover. In the early 2000s, researcher Henk Jonkers at TU Delft looked at concrete's most common weakness and asked a question that sounded almost naive. What if concrete could repair itself automatically? Nature already does this. Not perfectly, not instantly, but persistently. Microorganisms survive harsh environments and create minerals all the time. Limestone isn't just geology. It's chemistry and biology working together. So the concept emerged. Embed dormant bacterial spores in concrete. Keep them inactive during normal life. Let a crack act like a switch by allowing water to enter, and use that activation to produce minerals that seal the crack. The genius wasn't put bacteria in concrete. It was a control logic, dormant until needed activated by the same thing that makes cracks dangerous. Water ingress, and producing a mineral compatible with concrete chemistry. This was the moment the idea moved from science fiction to engineering hypothesis. But to become real, it had to pass two brutal tests. Can anything survive inside concrete long enough to matter? Can a repair product actually seal a crack, not just coat it? Concrete is porous. That's normal. But those pores and microcracks become pathways. When water reaches steel reinforcement, corrosion begins. And corrosion products expand, generating internal stress that worsens cracking. So the enemy isn't the crack itself. It's what the crack allows. Self-healing concrete aims to block the pathway early. The common bacterial approach works like this. Bacterial spores, often Bacillus species, are mixed into the concrete in a protective form. In concrete's harsh alkaline environment, active bacteria would die, but spores can remain dormant. When a crack forms and water enters, conditions locally change, and the spores can activate if the bacteria consume an embedded nutrient source and create conditions that lead to calcium carbonate precipitation, basically forming limestone-like material inside the crack. That mineral deposit can reduce permeability and seal small cracks enough to slow or stop further ingress. Important nuance. This is not the crack disappears like CGI. The goal is sealing, restoring durability, not making the material flawless. And it's not free. Nutrients are finite. Activation depends on water, and crack width matters, which leads to the most important question. How far can biology actually go inside a structural material? The counterintuitive part is this. Self-healing concrete doesn't need to fix everything. It only needs to stop the chain reaction. If the material reliably seals small cracks early, before they become highways for water and salts, then a bridge doesn't just look better. It lasts longer. That changes the entire life cycle. Fewer repairs, fewer lane closures, fewer emergency interventions, longer intervals between major rehabilitation, and less total cement poured over decades. So the wow isn't concrete that never breaks. The wow is concrete that treats cracks as a normal event and responds in a controlled way. But here's the cliffhanger. If the idea is so strong, why aren't we already pouring self-healing concrete everywhere? Because the engineering reality is harsh, and biology has boundaries. To make this work in real structures, engineers have to solve practical problems. 1. Survival and delivery. Spores and nutrients often need protection during mixing and curing. That's why encapsulation strategies exist. Microcapsules or porous carriers that shield bacteria until cracks form. 2. Crack width limits. Bacteria can't bridge large gaps. Self-healing tends to be best for microcracks and small crack widths. Beyond a certain size, you need conventional repair or different strategies. 3. Timescale. Healing is not instant. It can take days to weeks depending on temperature, moisture, and chemistry. That's fine for durability, not for emergency leaks. For finite fuel, nutrients can be used up. The material doesn't heal forever without limits. Self-healing is a design capability with a budget. 5. Standards and predictability. Construction is conservative for a reason. Engineers need repeatability, long-term performance data, and standards before widespread adoption. The real achievement isn't just bacteria mineralizing. It's packaging biology into a predictable, testable engineering system. Even good engineering ideas fail if they can't survive skepticism. And living concrete triggered skepticism instantly because concrete is supposed to be inert, predictable, boring. Jonkers and others had to prove the basics. Spores can survive the environment. Healing reduces permeability. Sealing improves durability metrics. The added cost can be justified by life cycle savings. That last point is where the story becomes real. Concrete is cheap. Anything that increases upfront cost gets rejected unless it saves money later, through reduced maintenance or longer service life. So the field's real challenge wasn't only science. It was translation. From lab specimens to field conditions, from look it healed to here's the measured durability gain, from impressive demos to procurement decisions. This is why self-healing concrete is evolving as a durability technology first, not a headline miracle. And that brings us to where it's actually being used. Self-healing concrete makes the most sense where cracks are expected access for repairs, difficult or expensive water tightness, and durability matter more than aesthetics, and life cycle cost dominates upfront cost. Examples of the kinds of applications it targets: water-retaining structures and basements, tunnels, and underground infrastructure, marine and coastal structures where chloride ingress is brutal. Industrial floors and slabs where downtime is expensive, epicast components where manufacturing quality control is tighter. The key idea isn't use it everywhere. It's use it where cracking is predictable and sealing prevents expensive downstream damage. And this is also where a related family of technologies enters the conversation. Materials that use biology to mineralize without being concrete in the classic sense. But before that, we have to face the tension point honestly. Self-healing concrete has real constraints. Cost. Today it often carries a premium. The business case depends on life cycle savings and avoided repairs. Crack size. It's not a solution for large structural fractures. Think durability insurance, not structural resurrection. Time. Healing is not immediate, so it's not a replacement for emergency intervention. Uncertainty and standards. Long-term field data is still accumulating, and construction adoption depends on codes, warranties, and consistent performance. There's also a communication risk. People hear living concrete and imagine buildings that grow like trees. That's not what this is. This is concrete engineered to reduce permeability after cracking, so the structure stays durable. Now the hopeful part. The field is improving quickly, and the breakthroughs are mostly unglamorous. Packaging, consistency, better carriers, better test standards. That's what moves a material from demo to default. Progress in self-healing concrete is coming from engineering, not hype. Better encapsulation and carrier systems so bacteria survive mixing and activate where needed, improved nutrient strategies to extend functional lifetime without harming baseline concrete performance. Hybrid approaches that combine biological healing with conventional crack control design more realistic testing. Permeability, chloride penetration, freeze-thaw durability, long-term cycling, early deployments and pilots that generate the data civil engineers actually trust. Also important, living concrete is part of a bigger ecosystem. Some companies and labs pursue biomineralization routes that create cement-like binders using biology, including algae or bacteria-driven mineral growth. That's adjacent, not identical, but it points to a future where construction materials may become lower carbon through new chemistries and processes. The main takeaway is this. We're moving from can it heal to can it be specified, certified, and financed? That's the real commercial threshold. In the next 5 years, expect self-healing concrete to expand mainly in high-value durability applications, places where avoiding repairs pays a premium. In 10 years, if field data and standard mature, it can become a normal option in infrastructure design, especially in environments where water ingress and corrosion dominate lifecycle cost. In 20 years, the bigger shift may be philosophical. Engineering won't only optimize materials for peak strength, it will optimize them for recovery and service life. Materials designed to handle real conditions, not ideal ones, not alive buildings, but infrastructure that behaves less like something that inevitably decays and more like something designed to resist decay through feedback. That's a quiet revolution, and construction is exactly the kind of industry where quiet revolutions matter most. Self-healing concrete connects directly to the future of materials. Self-healing polymer smart composites additive manufacturing, where microstructure is engineered biomimicry as a design method, not a metaphor. Carbon-aware materials that optimize life cycle impact, not just upfront emissions. This is a future forge pattern. The future is built when materials stop being passive. If you're a student or engineer, this field is a perfect lesson. A breakthrough isn't one lab demo. It's a chain, mechanism, repeatability, standards, field performance, adoption. Self-healing concrete is still crossing that bridge. And if you're simply curious, this is one of the clearest examples that biology isn't just for medicine. Biology is becoming an engineering tool. So here's the question. If we can give concrete a controlled self-repair response, what other dead materials are next? Concrete built the modern world, but also quietly drains it through maintenance cycles, repair budgets, and emissions tied to constant replacement. Self-healing concrete won't end cracking, but it can change what cracking means. From the start of failure to a manageable event, the material is designed to survive. That's the deeper future forge idea. The future isn't only stronger materials. It's materials that keep functioning when reality happens. If you want to understand the materials shaping tomorrow before they become normal, subscribe to Future Forge Explored, because next, we can go deeper into the second half of this story. Not self-healing concrete, but carbon-negative binders, the race to make cement without the climate cost. And once you see that landscape, you'll realize the buildings of the future won't just stand there. They'll be engineered to last.